Good evening, good morning, good afternoon, whatever it is, wherever and whenever you are watching. Today, the problem that we're going to be solving is redundant connection. Redundant connection. So, let's just first read this problem and understand what it has to say. So, in this problem, a tree is an undirected graph that is connected and has no cycles. You are given a graph that started as a tree with n nodes labeled from 1 to n with one additional edge added. That means that it was initially a tree and then just exactly one extra edge was added. One extra edge was added. Then the graph is represented as an array of edges. Oh, sorry, I forgot this. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed, meaning that if it was already a tree, the edge that was added is not an edge that was already existent. It is not a like it's not a self edge also, like 2 is connected to 2 itself. It is not like that also. So it is just an extra additional edge that is added into the tree. The graph is represented as an array of edges of length n. The length of the edges is n. That means it is given that the number of nodes is equal to the number of edges, right? And where edges at I indicates A to B, where A and B are the edge between nodes A and B. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the last one that occurs. So these are the examples. Let me go through them very quickly. So let's say this was a tree. This was a tree pehle. This was a tree where this additional edge was added. This additional edge made it something else. Like this additional edge was added. Now I want to return this edge. Right? So see, I want to return the edge that can be removed so that the resulting graph is a tree of n nodes. I want to make this graph again a tree. And if there are multiple answers, I need to return the last one. So here, if I remove this edge also, it would become a tree, right? It would become a tree, because if you see this, this is also a tree, right? That is also a tree. If I remove this, that is also a tree. And if I remove this, it is also a tree. So which one do I have to remove? That your question would be straightforward. They have given it that remove the last occurrence. So here 1 2 was this, 1 3 was this, and last was 2 3. 1 2 1 3, last was 2 3. 1 2 1 3, last was 2 3. So I need to remove this. So essentially what we're doing, let's just see the second example. Here also this was a tree. How did the tree look? The tree looked somewhat like this. And then this edge was added and it made it a graph, right? So this is the tree that we need to return. Now here you can remove this also, you can remove this also to make it a tree. But how do we decide what do we have to remove? We need the last occurrence. So what was the last occurrence here? The last occurrence was 1 2, 2 3, 3 4, and 1 4. This made it a loop. So we need to remove 1 4. So what is the very, very basic approach? So whenever you hear graph, the word graph, in an interview, in a CP contest, anywhere, the first thing that comes to your mind is DFS, BFS, right? That is the first thing that comes to your mind. So let's just go with that. What essentially is DFS and BFS? How do we use here? DFS means depth first search. We go each neighbor, and we check neighbors, right? So initially for the DFS, we need an adjacency list. So adjacency list would be like 1's neighbor are 2 and 3, then 2's neighbors are 1 and 3, and then 3's neighbors are 1 and 2, right? So now we go through each node and then their neighbors, So how would we structure this DFS? What do we need to do? We need to check for cycles, right? So we need to check for cycles. So let's just construct this graph edge by edge, while building this. So what do we have to do? Let's say we started out with just nodes. And we build it. We start with 1. 1 had edge 2 and 3. We check whether a edge already exists between a given graph. We start with 1. 1, 2. 1, 2. Does 1, 2 exist? The question had 1, 2, 1, 3 and 2, 3. 1, 2, 1, 3 and 2, 3. Right? So we start with this. We start here. 1, 2. 1, 2. We go DFS. We do DFS. Our adjacency list right now is just empty, right? It is just empty. So 1, 2 is adjacency list. Does there exist anything? No, the edge does not exist. That means 1 is not connected to 2 anyhow. The 1 is not connected to 2 anyhow. So we add this. So 1 is connected to 2, 2 is connected to 1. We add this. Now we go 1, 3. 1, 3. So we start with 1. And we need to check if this exists. 1 and 3. Does this exist? We start with 1. Who is 1's neighbor? 2. We go down with DFS to 2. We check 2's neighbor. Who is 2's neighbor? 1. Is 1 already visited? Yes, because we started with 1. And then next neighbor is nothing. 2 does not have any other neighbor as of yet. So that means that 1 and 3 does not have any edge as of yet. 1 and 3 are not connected. So we connect them. 1 has 3 and 3 has 1. We connect them. There you go. We connect them. Now we have 2 and 3. So we start with 2. We go to their edge. We start with 2, mark it as visited. Then we go to its edge. Next neighbor, we go to 1. Because 2 has only 1 as its neighbor. Then we go to edge 1, mark 1 as visited. Then we check 1's neighbors. We had 2. Just a second. Yeah. We had 2. 2 was already visited. So we skip it. Then we go to 3. This had 3 here. We had to add an edge between 2 and 3. But somehow, when we started from 2, we visited 3. That means the edge 2 and 3 causes the redundancy, causes the cycle, and hence we return this. This is how the DFS would look. We will start by building the graph step by step. Now this is the brute force. I hope you all will be able to do that. If not, you can ask in the comments. I will share the code inside the comments if anybody asks. Then let's just go to the most optimal approach. What do you think the most optimal approach is? Now, in one of my video, I think the very first video, I had mentioned whenever you hear the word graph, 3 things should come to your mind. Let me just say it again. Whenever you hear the word graph, 3 things should come to your mind. First thing, DFS. Second thing, DFS. I just told that. DFS. And the third thing is union find. Now basically this is also called as disjoint set. Now this is not any method as such. This is not a method. This is a new data structure. This is a new data structure. This is a new data structure that we'll be using. So essentially what we are doing right here, right now, is that we are checking if we were checking if 1 is already connected to 2. It was not, hence we added this edge. We were checking if 1 is already connected to 3. If it was not, then we added this edge. We were checking if 2 is already connected to 3. 2 is already connected to 3. If not, then we were going to add. But since it was already connected like this, hence this was our answer, right? This we did using DFS. We used O of n time complexity per se, somewhere about O of n, because we are traversing each node, right? We had linear time complexity. O of n does not exactly mean O of n. I mean linear time complexity, because DFS is always linear, right? This was linear. Now when we use the disjoint set, we can do this in O of 1. We can do this in constant time. What is this magic? Black magic. How can we do this? How do we know that 0 1 is connected to 2 in constant time? How? Just how are we doing that? So let me explain. So if I take this as an example, this tree as an example, what we are doing essentially is path compression. What we are doing is path compression using union find by rank. I think I had to write that like this, not in temporary pen. Path compression, we are doing path compression using union find by rank. Now how do we do that? Now what exactly is union find? What exactly is union find, and how exactly do we achieve this? Like, how do I know that 4 is already connected to 1? How do I know that? Right? How do I know that 4 is already connected to 5 without traversing this entire thing? Right? So basically what union find does is it maintains two things: a rank of each node, and parent of each node. Right? Parent, what do you mean by parent? 4, 3. 4's parent is 3, 3's parent is 2, right? So 4's parent is also 2. We are here currently concerned about the super parent, right? We are here concerned about super parent. So if you see, what we are doing in union find is that 4 is connected to 3 is connected to 2, and 5 is connected to 1 is also connected to 2. So we can just compress its path. Path compression comes here. We can compress its path. We can just have everything connected to 2. And then if we know that 4, now here after completing union find, our super parent would somewhat look like everybody's parent was 2 here, right? So in constant time we can see that we can just access here that 4's parent was also 2, and 5's parent was also 2, and hence there exists an edge, and hence that is our answer, right? I'm not talking about this question. We can just say that hence 4 is connected to 5 somehow. We just want to know that, right? While building this up, we just want to know whether this is connected to this somehow while loop, right? In some loop. So how are we gonna implement that? What is rank? What is super parent? What is all of this? What is rank? I explained super parent. Super parent means where it is connected, the topmost one, the big guy, the Raja, the king, the Don. This is the Don, right? If everybody is connected to the Don, essentially they are connected to each other as well. That is what union find does, and this is called path compression. Like this is connected to this, then this is also connected to this, and we just remove this off. Now disjoint sets are used only when we want to know whether something is connected to something, because that is where it excels. Constant time instead of DFS BFS O of n, linear time, right? So let me explain what is a parent, and I explained what a parent is. Now what is a rank? Initially every rank is 1. And every 1 2 3 4 5 and everybody is their own parent. We are essentially building up the graph one by one. Why is everybody's rank 1? 1 2 3 4 and 5, right? Everybody, let's assume, is connected to their own self, right? Now let's just start, and I'll make you all understand how the rank system works. Okay, so initially everybody is their own parent and everybody's rank is 1. What is a rank? I am still yet to explain. I will explain it on the go. Okay, so now I start here. Okay. Okay, so I start here, and let me just copy this down. My edges. Okay, these were my edges. Now let us start building this graph. Okay, let me bring this a little down so that things are more clearer. Okay, so we are building this graph edge by edge. Now we are maintaining this rank and super parent. So now we have edge 1 and 2. Now we check who is 1's parent. 1's parent is 1 itself, and 2's parent is 2's itself. What is the rank of 1? 1. What is the rank of 2? 1. Okay, so it as a rule of thumb, whoever's rank is low gets connected to whoever's rank is higher. This is very important. Okay, so now when the ranks are equal, it clearly does not matter. It just does not matter. So we had 1 2. So we start with this. Now super parent of 1 was 1, parent of 2 was 2. Both of their ranks were same, so it essentially does not matter who is who, right? So we connect two to 1. Now since it is going one step deeper, so the rank of 2 is increased by the rank of 1. Was 1, so it becomes 2. Right, because this is 1. Now please note, it is not the height. I will explain again. It is not the height. Let me just write it down here. Rank is not height. I'll highlight this in red. Rank is not height. Okay, so rank is not height. So now 1 and 2 are connected. Right? Now we updated the rank. What did we do? Rank of higher, right? Essentially, what did we do? Rank of higher plus equal to rank of lower, and parent of lower is equal to parent of higher, right? So now here we considered low as 1, and hence let me just get this more. Why am I writing it here so close by everything? Anyways, so we updated the rank of 2 to 2, and we update the parent of 1 of the lower to the parent of 2. That means parent of 1 is also 2, because 1 is obviously connected to 2. We go to the next edge, 2 comma 3. What do? We get the parent of 2 and get the parent of 3. Who is the parent of 2? 2. Who is the parent of 3? 3. Who is the parent of 2? 2. Who is the parent of 3? 3. So now what do? We check their ranks. Who is the lower rank? Lower rank is 1. Lower rank is of 3. Lower rank is 1 and it is of 3. So what do? We connect 3 to 2, right? We connect 3 to 2. We connect 3 to 2. Again, what do? Rank of higher plus equal to rank of lower plus equal to rank of lower. So here rank became 3. So the rank was 3. Then we update the parent. Of 3 to, again, who was the parent? 2. 3's parent was also 2. So this is done. 3's parent was also 2. We updated the rank of 2. Then we go to the next edge, that is 3 comma 4. The parent of 3, we get the parent of 3 is equal to 2, and the parent of 4 is 4 itself. So what do we do? We take the one with lower rank of 3. The rank of 2 was 3, because the parent is here, and the rank of 4 was 1. So again we connect 4 to 2 again, and then we update the ranks. So we update the rank of higher with the rank of lower, and then we again update the parent. Now we see who is, now we take this. Who is the parent of 1? 2. Who is the parent of 4? 2. Since both are same, that means they are already connected. And hence they will form a cycle. And hence we return 1 of 4. We return 1 of 4. So I hope you all understand that. Rank is not the height. Rank is to whom are most of it connected. Now I hope you all understood this example. Let's quickly code this up. So find redundancy. Firstly we will get int n is equal to edges.length. We got our edges.length, we got our n. Then we initialize a parent new int n, then we initialize a rank matrix, rank array, then we loop through each of these edge, then we loop and initialize the parents and ranks. Int I is equal to 0, I is less than n, I plus plus, and then our parent of each is itself and our rank of each initializes as 1 because they are connected to nobody. Then after that we loop through each. Int I is equal to 0, int I is equal to 0, I is less than n, I plus plus, int x is equal to edges at I at 0, and int y is equal to, that means we are just taking the start and the end of the edge, placing them in one variable, and then we find if not union of x comma y comma parent comma rank, if they are not true union, then we return edges of I. So basically what the not union thing does here is essentially that it tells us that if they are already connected, then we will return, and if essentially nothing is returned, then we will just send an empty array, like we just fill it with 1 and then send it, because essentially everything is gonna work here. But since we return something inside the function, we have to, otherwise Java will throw an error. So now basically let us do union find. What exactly is union? Private boolean union int node1, int node2, integer array parent, integer array rank, int parent of 1 is equal to find parent of 1, we find the parent of n1, and int p2 we find the parent of n2. Now what did we do next? If p1 equal to p2, that means both of them have the same parents, then we return false. Otherwise we check what was our this, that higher rank. We check for higher ranks, right? If rank of p1 is higher than rank of p2, then what did we do? We did rank of higher plus equal to rank of lower, and parent of lower becomes the parent of higher, that is p1. Otherwise we do the exact opposite. That is higher would be p2 and lower would be p1, and this will be this, right? And then we return true. Now we need to define the find function. Define int find, int n, integer array of parent. If n not equal to parent of n, then we assign the parent of n is equal to find parent of n comma parent. Otherwise we return parent of n. This essentially, what it does is it compresses the path. This is the function which compresses the path. So now if you see, when we find when we find n1, so let's say I had the edge, first edge, we go to n1, find for 1, for node 1, node 1 is equal to parent of 1 because they are initialized with itself, initialized with itself, right? Since node 1 is equal to parent of 1, we return node 1, so the parent p1 would be again 1 and this would be 2, then it gets added here, and the parent of 2, parent of 1 became 2, parent of 1 became 2, we just saw that, right? The parent of 1 became 2 and this was updated to 2 and this was updated to 2, right? That is essentially what is happening here, and we are finding path compressing here, because if somebody else's parent was somebody else, then we have to recurse, like we have to return, like we have to go to the top, we have to go to the top, right? We have to go to the top, right? If somebody's parent is somebody's parent is somebody, till we find that ultimate boss. Who is the ultimate boss? Who is the parent of itself? Parent of itself is this, right? This equation shows us the parent of itself, so we have to go till the ultimate boss and then return down and save its parent, right? So we are going to the ultimate boss, we get the ultimate boss here, and then if not, then we return. When we find this, we return, save it as the ultimate boss, then we return, save it as the ultimate boss. That is what we are essentially doing here, and hopefully this works. Okay, it did not work because apparently this is not a statement. Line number 33, int is equal to 0. Wow, wonderful. Josh is so smart. Okay, this is on line number here, line number this. Okay, let me debug it. Okay, so I made a very small mistake, not really small, but it's kind of a big mistake, because since you just saw we are not keeping our array 0 indexed, so we need to create something, right? We need to create an array that is greater by 1, then we have to assign it like this, right? We have to assign it like this, and then when we run it, it should hopefully work, and there you go, that it ran, right? Since it was not 0 indexed, we had to create a size bigger by 1. Okay, so I hope you all understand the disjoint set data structure. It is basically used when we have to find a connection between something and something, so we compress the path to the ultimate boss. Let me just write it down. Ultimate boss. We have to compress it down to the ultimate boss, and then we find if any two are connected to the same ultimate boss, then they already have a path exists, and then hence this connection was not needed. I hope you all understood this problem, and thank you so much for watching, and have a great day.